Okay, guys, resonance. Resonance. Questions about resonance? Pretty much match. I think there was a homework question out here. Total number of p orbitals. Total number of p orbitals here. 10. 10 p orbitals. Number of pi electrons. Uh-huh. 10. Bond order for each carbon-carbon bond. It's actually all these. It's 1.5 for every one. All of these 1.5. That one, that one, that one, that one. Okay. All through there, all through the pi system, it's 1.5. That could take a little bit more understanding and discussion. How about this bond order right here? Carbon-carbon bond order. One, just a single bond, yes? How about here? 1, yes. Again, the bond order here, 1.5, it's a little bit not as intuitive as when we do charges. When we have a charged species, which is on the next page, we're looking at cations. But again, these are the types of questions we need to be able to address. And so, as we go along, they should hopefully become more clear. Cations. Okay, now we have polarity, we have charge. This helps us sort of guide our electron movement, guide our resonance thinking. How do you stabilize a cation? Do you move electrons towards it or away? Towards it. Everything wants to be towards neutral. Electrons, we can move these electrons over. Windshield wiper, did I say that last time? A windshield wiper over, and we get that resonance structure. Which one's better, the one on the left or right? And they have the same energy, same stability. What does the resonance hybrid look like? The resonance hybrid is a blend of your resonance structures. Between carbon, do we label these A, B, or C or anything? A, B, C. Between A and B, single bond, double bond. What's the blend of single and double? What's the average? 1.5. What's the average of double and single? 1.5. Yeah, we drew this last time. Charge. What's the average of +1 and neutral? Partial positive. What's the average of neutral and neutral? Neutral. What's the average of neutral and positive? Partial positive. If you could look at this compound here, this molecule, this cation, and if you could really look at it, that's what it would look at like over there. These electrons are really spread out in here. It's one pi system. Pi system consisting of how many p orbitals? 3 p orbitals, right? If an atom ain't got a p orbital, it ain't doing resonance. I mean, you can see the p orbitals here better. It's just empty here. How do you make a pi bond? 2 p orbitals interacting. There's got to be a p orbital here. It's here. It's empty. It's empty in this fake structure. In real life, it's participating in one pi system, and it's got It's got 2 electrons in that system. It's like a garden hose that has some water in it. The water is all in there. The electrons are all in here. Okay, we can draw this, right? 3p orbitals, right? Don't draw this. 1 electron empty. Well, that's the original structure, right? Again, you can put these electrons in here any way you want. What we have is 3p orbitals and there's 2 electrons in here. They're spread out in here. It's hard to really show that. We're showing it various ways. Trying to show just all orbitals, showing fake structures, which we should show and call them resonance structures. This is probably the best way, or perhaps it's called the hybrid. But when you draw the hybrid, you typically don't draw the orbitals. It's all getting at the same thing. 1 pi system, the electrons are spread out in there. What do you need to be able to do? Well, one thing is you need to be able to draw your resonance structures. That comes from arrow movement. Arrow movement, like mechanism, arrows guide your movement between structures. Resonance arrow, charges. One key thing about resonance is it delocalizes the charge. This charge is not just right there on that carbon. Compare it to this cation with no pi bond. This cation is much more stable than this one. Why? It's resonance stabilized. What does that do? Resonance delocalizes the charge. Remember, this is not the true structure anymore. This carbon only has a partial positive, where this carbon has a full positive. Which is better? Partial positive is better. Less charge. The charge has been delocalized by resonance onto another atom, and the charge is being shared. There's no resonance here. There's no p orbital here, here, or here. There's no p orbital in this molecule. I'm sorry, that's wrong. It is still sp2. There's an empty p orbital here. Okay? That is sp2 with an empty p orbital. There's none here. That's sp3, sp3. What is that p orbital interacting with, or overlapping with, or conjugating with? Nothing. Can you draw another resonance structure of this where we only move pi electrons? That's impossible since there are no pi electrons in this compound. Am I right? There are no pi electrons. There's 1 p orbital, but there's no pi electrons. If there's no pi electrons, you certainly can't be doing resonance. This would be called, what we had here would be called a isolated cation, or non-delocalized. Delocalized cations, much better. Okay, resonance here. The carbon next to your benzene ring is called the benzylic carbon. Cation here would be called a benzylic cation. Benzylic cations are very stable. Why? Right, resonance. Okay, can you draw resonance structures here? You can draw multiple resonance structures. Draw first one. How do you stabilize a cation? Move electrons towards it or away? Towards it. The old windshield wiper. These electrons can move here. Either line could be considered the pi bond. Windshield wiper over. We now have double bond there. Positive here. And we did not do anything here or here. And everything has to come from the arrow movement. Why? Because that helps you. You use your arrow movement, and then you say, okay, what does this give? It gives F. Okay, can you draw another resonance structure? We can windshield wiper this back, but that just gives us back this. What else could we do? this up, move these pi electrons up, and windshield wiper it up. I'm unable to draw a ring. Okay, we can windshield wiper these over here. Yeah. And then we can windshield wiper these down here. Everybody there? Yeah? And we get back the original. Now, we got to talk about this a little bit, the benzene ring. Is it original? I call it original because the charge is back on the benzylic carbon. But there is a slight difference here. The pi bonds have been moved. Here the pi bond is between these two carbons, or there it's between these two carbons, but over here it's not between these two carbons. So the original and this one are different resonance structures. Don't do this in your notes. We could just, I can move these here, I can move these here, and I can move these here. And that would give Roman numeral 5, if that's 1, 2, 3, 4, and 5. Okay? Does everybody agree that that arrow movement would give the one on the end? Yeah. That's a resonance structure of benzene. I'm not considering that as a different resonance structure because really one of the main things we want to focus on here is delocalizing the charge. The charge is delocalized to that carbon, to that carbon, to that carbon, and then I said it's back to the original position. And sometimes you may be asked to show resonance structures in which the charge is delocalized. Thus, you really wouldn't count the one on the end because it's the same place. Okay. Benzylic cation, very stabilized because it's delocalized a lot. The charge is really spread out, and that's a better thing than if the charge is just isolated. Orbital view. We have an empty p orbital here. But then every atom in the ring has a p orbital. One electron in each orbital. And you can draw, how do we draw a pi bond? Do we draw it between here, here, and here? Or do we draw it between here, here, and there? Well, either way works. That's why either this or the one on the end works. Basically, the pi system is all these are lined up. Once they all line up, they becomes one system. And that one system has 6 electrons in it. And the electrons spread out all in there. Just like water in a garden hose spreading out. And thus, there is electron density in this area. For electron density to be there, that means some had to come from over here. If some comes from over here, it leaves positive charge over here. And we start seeing the positive charge develop. What does the hybrid look like? Well, it gets back to what we did. What's the blend of, look between here and here. That's a single bond. But it's got double bond character as well. Back to single. What's the blend of single and double? Again, we're not going to say, well, it's got more double than single, so it's more than 1.5. If it's between 1 and 2, we're just going to say 1.5. Okay? So it's 1.5. But guess what? If you look at every carbon-carbon bond, it's a blend of single, single, single. Well, maybe that one is important, because now it's double. That is important for doing the blend. And since it has more than just single bond character, it has some double bond character. It's more than 1, but it's less than 2. Basically, if you look at this, it's 1.5 all the way around. Charge, partial positive here, 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 and here. That comes from blended in resonance structures. If you can look at this cation, it would look like that right there. So again, it's the same type of questions and considerations. And this is supposed to be a lot like, okay? This is resonance. Whenever you have possibility of resonance, any one structure is no longer truly representative of what's going on. And I call it fake. That's an overstatement. True structure becomes a blend, a composite, a hybrid of those that you can draw. It becomes this sort of blend. It becomes harder to draw. Okay, this is the same statements we'll keep making over and over. Stabilization by a lone pair. How do we stabilize up there? Stabilization by carbon-carbon pi bond. Okay, now stabilization by a lone pair. Take a look at this cation. How can we stabilize it?
Lone pair of ions.
Seems like a lone pair. Okay, how do you stabilize a cation?
Electrons.
Move electrons towards it. What electrons do we have? These electrons can move in here. And what does that arrow movement give? Lone pairs falling in to make pi bond. It's not jumping over here to become lone pair over there. That is giving this here. One lone pair left on oxygen. And charge now is, oxygen is now positive. Yeah, is that a resonance structure? All we did was move pi electrons. What's hybridization of the oxygen? sp2, why? It's got 4 regions around it. Goes back to the exception we stated week 1. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Is this lone pair next to a p orbital? Mm-hmm. Yeah, an empty p orbital over here. By the way, if it wasn't in a p orbital, we should not be drawing resonance structure. Yeah, it's p orbital. If we look at the orbital view, we have an empty p orbital here. The fact that there's p orbital there, empty or not, makes one of these lone pairs want to be in a p orbital, and the other is in a hybrid, and the 3 lines are supposed to represent trigonal planar with a p orbital left over. That's sp2. Why does it want to be in a p orbital? So it can interact with the neighboring. And what are we starting to get? A pi system of 2 p orbitals and 2 electrons. And the electrons are spread out in here. So some of this electron density is actually on the carbon as well. That doesn't show that. but this does. So what does the blend look like? That's sort of the orbital view, the blend without orbitals. Oxygen, yeah? What's the bond order between the O and the carbon here? It's a blend here. Yeah, it's 1.5. It's like this. What's the charge on this carbon? Partial positive. On the oxygen? Partial positive. If you could look at the structure, that's how it looks like over there. Which resonance structure is major? That is the best? Which one you like the best? Somebody said it. I thought someone said it. Somebody didn't say the one on the right? One on the right. Why is that the best one? More bonds? More bonds? Yeah? Bonds is a better thing. We can also say all atoms have octet. Is that true? In that structure, does all atoms have an octet? Yeah. Where over here, the carbon did not have an octet. Only 3 bonds, 6 electrons around that carbon. It's a better structure. What's not as good about the structure on the right? What do you not like about it? Positive on oxygen. You'd rather have positive on carbon. Carbon's more of an electropositive atom. Oxygen's more electronegative. Yes, that is a not as good thing. But these things outweigh that. This is major because of these things. Oxygen doesn't mind being positive. Actually, none of these over here, chlorine, even fluorine, doesn't mind being positive as long as it has an octet. Does that oxygen have an octet? Yes. What is not good is to have a positive oxygen or fluorine or chlorine and not an octet. If you show that, the oxygen or fluorine will hunt you down and make you pay for it. All right? They don't like that. It doesn't mind sharing as long as it keeps its octet. So that's a major structure, and this is actually minor. The charge is delocalized. Question: in the hybrid, we said partial positive, partial positive. Which of these atoms has more positive? Which of these has more positive, oxygen or carbon? It comes from your resonance structures. Which one contributes more to the blend? If I'm making a blend of chocolate and vanilla ice cream, and I say the chocolate contributes more, the blend is going to have more of what flavor in it? Chocolate. Okay. Which one contributes more?
Oxygen.
The major one. That's what it means. It's the major contributor. Okay? And the charge is on oxygen. That means the blend is going to be more of the positive on oxygen, right? I didn't distinguish between them in my blend, but if we were asked, we would say, more positive on oxygen. I see that from my resonance structures. And knowing that, okay, this is like the kid. This is mom and dad. And we say the kid looks more like mom because mom is more stable. Okay? That's what major means. It's more stable. It's the best in terms of energy. And so the kid looks more like the major one. Question?
In your analogy just now, which one did you say was, in your analogy just now, which one did you say was the kid and which one did you say was the parents?
Well, these are the parents. And they blend to make the kid. Sometimes the kid looks more like mom, sometimes the kid looks more like dad. Sometimes the kid is an equal blend. In this case, the kid looks more like mom because mom is the major one. That's what major means. It's a major contributor to the hybrid. It's the major, it's the most stable. That's why it is the major. The charge has been delocalized by resonance. Stabilization by a lone pair. Okay, resonance structures here. You can draw more than one additional. I have a lone pair that's conjugated. This lone pair is in a p orbital. Many ways you can approach this, or you just know I can move these electrons in. We get that resonance structure there. Resonance arrows, right? These were already drawn in for you. What other resonance structure could we draw? Show here. Yes, that's an A arrow going that way. We could have also done a windshield wiper and gone this way. We could have showed that resonance structure. Of the three on the board, which one's major? This one here. More bonds. Everything has an octet. But the charge has been delocalized. The charge doesn't just sit on this carbon. It's delocalized onto that carbon. It's also delocalized onto the nitrogen. And a larger percentage of the positive charge is actually sitting on the nitrogen. Number of p orbitals. How many p orbitals we got here? 4, yeah. Pi electrons. Four. Got to be able to understand the structural aspects of that. Resonance can help guide regioselectivity of reactions, such as alkene reactions. If you react this alkene with HBr, which product are we going to get? Well, the question comes from where are you going to make cation, top or bottom? It's actually going to be bottom. We can attack up, and this is going to give UH up, cation here, nitrogen here. Why is that a good cation? Resonance. We can draw a resonance structure. All right, I'm not going to draw it. You should be able to draw it. Yeah? If we had reacted the other way and put H down here, cation at the top. Question, top or bottom? Well, that's if we did it at the bottom. That's if we put the cation at the top. Alkene reaction, yep. Is that carbocation resonance stabilized? No, there's no resonance there. Is there a p orbital next door? No, there's two H's there, tetrahedral, tetrahedral. There's no p orbital. That's an empty p orbital with its overlapping with nothing. If it's not overlapping with any other p orbitals, then how can it get electron density through a resonance? It can't. There's no connection. Okay? So we have a resonance delocalized cation. That's going to be the best. I'm going to draw this because this arrow movement gives this, yeah? There's your carbocation. One thing you have to understand is this is one carbocation. I circled one carbocation. Right? But there's two structures there. Yes, I'm showing two different structures to help illustrate the one carbocation that's formed. The one carbocation is the hybrid. I could have 5 resonance structures. It's still only one carbocation. All right, you got to remember that. This carbocation or that one? Well, this one's better because it's delocalized. Then what? How do you get final products? Br minus attacks cation. You can always work with any resonance structure. We could take this and add it to the cation. That gives us the product. Which is the product? Here? Yeah. You can always work with any resonance structure. We could work with this one. Neither one of them is actually correct. True structure's in between. So why can't we work with this one? Actually, this is closer to the true structure of the hybrid, right? Isn't this the major one? How would you react this to get to the final product? Well, same thing. These electrons add here, but instead of just making a bond to cation, what do we have to do to get final structure? We have to move these back to the nitrogen. And does this arrow movement give the structure on the right? Yes. You can always work with any resonance structure. All right? So, regioselectivity. Resonance can guide the regioselectivity. Down here, you can do this one on your own. Which product will be major? Or most? Anions. How do you stabilize an anion? Move electrons towards it, or do you need to move electrons away from it? Away from this carbon. It's got too many electrons. How can we draw resonance here? Start here. Lone pair is a great place to start when you're doing resonance. These electrons can move in here. But that carbon already has 4 bonds. It can't make 5, but these can move out. And I reckon I call this the old in and out. What does my arrow movement give? We now have double bond here. What's on the end carbon?
Lone pair.
Lone pair. What's the charge now? Because one of the golden rules says all resonance structures should have the same net charge. This carbon is now negative. How many H's on that carbon? 2. Still 2. Because when you do resonance, you don't move any atoms, right? Which one's best, left or right? Same energy. Bond order between each carbon. 1.5 exact. Charges. Partial minus, partial minus. If you could look at this anion, it would look like that over there. Equal electron density between each carbon. Exactly equal, because the resonance structures are exactly equal contributors. You don't say one's major, one's minor. Equal contributors. These are easiest to blend. Very equal hybrid. Okay? Look at this structure. Which bond is longer? A to B or B to C? Which bond is longer? AB or BC?
BC.
Which one?
BC.
BC? Why BC?
Are they both SB2?
Both carbon-carbon bonds are the same length. I thought we just said that over there.
Yeah.
Bond order equates to bond length. It's basically telling you your bond. The bonds are identical. They're both at 1.5 exact. It's an exact blend. Oh, you guys were looking at the fake structure. Don't assess fake structures, assess real structures. The real structure is the hybrid. Right? Which bond is longer, AB or CD?
CD.
CD is longer. It's sp3, sp3. I mean, yeah. Single bonds are typically longer than double bonds. There's no resonance here. This is not a delocalized pi bond. Can we move the pi bond here? I see this a lot. Here we go. Resonance. Let's move this here. And let's do boom, 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 boom. That would put positive here. And double bond here. There we go. Nice resonance structure. I just windshield wipered them over. How many rules did we break here? I see at least 3 rules we broke. First off, there's 2 H's here. That means we have a carbon that looks like that, and that's horrendous. Carbon with 5 bonds. Did you recognize that? There's 2 H's here, right? Is there a p orbital here? That's sp3. There's no p orbital. So how are we doing resonance? I don't know. This is net neutral. All of a sudden we have a positive charge. There's so many problems there. Okay. That's an isolated double bond. Yes, double bonds tend to be shorter than single bonds. But we have resonance going on here. We have a blended, a hybrid structure. Each carbon-carbon bond is the same exact length. Okay, anion here. This is the anion of phenol. If there was an H here, that'd be phenol, right? I mean, that's phenol. Phenol has good acidity. Why? Because the anion is so stable. Why is it stable? Resonance. You need to draw resonance structures of phenol. By the way, what do you want to call this? This is called phenol, right? You know that? What do you want to call the anion of phenol? Well, let's see. What do you call this here? Name?
Hydroxide.
Why hydroxide? Oxide is O minus. Oxide is O minus, or 2 minus. Why hydroxide? Hydrogen oxide, hydroxide blend. Okay, this is phenol oxide. What do you want to call it? Yeah, draw resonance structures of the phenoxide anion. We got an anion. How do you stabilize an anion? Yeah. What does resonance do for the anion? Up here, the charge is not just on that carbon. The charge is delocalized onto another carbon. We spread the charge out. That's a stabilization. Can we spread this charge out? These electrons move here. Pi bond moves out. Yeah, look good? We can keep going. These electrons can come in here, and pi bond can move out. Again, it doesn't matter which line you consider as a pi bond. I just drew it out here. One of these is coming out here as a lone pair. Here, these electrons can move in here, make pi bond between here, but one of these has to move out. I reckon I'll do it this way. Move them back onto the carbon as a lone pair. Yeah? What can we do? What if we keep going? Electrons here and move these back out. That's pretty much the original. We discussed that before. The charge is now back onto the oxygen, yeah? But the pi bonds have been moved around. So when we look at this anion, it's not just localized on oxygen, it's delocalized onto 3 other carbons. That carbon, that carbon, that carbon. Resonance delocalized anion, more stable than if it was not. Phenol, pKa of about what? Regular alcohol, no p orbitals. Cyclohexanol, pKa of what? Similar to water. 16. Phenol, pKa of about 10. Plain, simple phenol. It's 1,000,000 times more acidic. Why? We consider the conjugate bases. Resonance delocalized. If you look at the conjugate base here, does that have any resonance? No resonance. You can't draw resonance structures there. The only thing this has going for it is that at least it's an oxygen anion and not a nitrogen or carbon. More acidic because it's resonance delocalized anion. Resonance in neutral molecules with heteroatoms. Well, that's what we have here. It's a neutral molecule. Heteroatom being non-carbon. Nitrogen is a heteroatom. We started with neutrals, and I said they're kind of hard to deal with because you don't have a charge. See, with these charges, we have a starting place that we can kind of hone in on and go from there. This guy, though, has a lone pair, and a lone pair is a great place to start doing resonance. As long as the orbital, as long as the lone pair is in a p orbital, as long as it's conjugated, is that lone pair conjugated? Yes, that lone pair is in a p orbital. Because anytime a lone pair is next to a pure, it's going to want to be in a pure. It's conjugated. Thus, we can do resonance here. We can start with a lone pair. These electrons can move here, and these can move out. And that gives Is that right? What's wrong with my structure?
Charge.
This is charge. This is net neutral. That better be net neutral. It looks like it's minus right now. Well, it's net neutral because that nitrogen is positive. This is going to be a lot like was just up here. Except up there, everything was a minus. Okay? Because now we can keep going. These electrons can move here, these can move out. Am I going to keep going? It's just like above. Here. I'm going to keep going because we need to ask a couple of questions. Pi bond here, yeah? We didn't do anything there. And these electrons can move here, these can move out. I can't always connect bonds in my rings. Everybody see the ring though? What's the name of this compound? Aniline. Aniline. Which carbons of the benzene ring of aniline above are most electron rich? Okay. Somebody shows you aniline and asks you which carbons of the benzene ring are most electron rich. What would be your answer? Comes from looking at your resonance structures. Which ones are the most electron rich? There's a blend here. In the blend, this is partial minus, partial minus, partial minus. Now, I'm not showing blended double bonds. I'm not showing partial bonds or anything. But the question was which ones were more electron rich. We see that in the blend, there's going to be minus on that carbon, and that carbon. Those are your electron-rich carbons, the ones where the minus falls. So that's the type of understanding we need to have. Again, assess your resonance structures. They tell you about the hybrid. Questions below. Okay, so we're at this point out, the rest of the handout are types of questions you need to be looking at, figuring out how to answer. What's the question really asking? And then answer it. We'll see how we doing. Let's see. And then the handout goes back to acid-base chemistry. You should pull out your acid-base handout. We had a page of resonance there. Okay? Look back at that. That's what we're doing now. But that's where we introduced it with some sort of elementary concepts. But the rest of this handout goes back to acid-base chemistry using resonance. Pull out your old handout. See some of you this afternoon. Have a good weekend, guys.